So maybe it has found some association between merging and non-core core, and I find this really interesting. Okay, and so this work has been published at MNRS. So please check it out if you want to find more details. And okay, next, I want to look forward a little bit. So machine learning has been widely used to solve a lot of astrophysics problems, but so far I have to say most studies have been like ours have been using simulation data for training and testing. There's a huge gap to apply machine learning to real observations because there are some really serious difficulties. First of all, in real observations, you don't know the ground truth. For example, you want to train a network to predict cluster mass. Even you use weak lensing mass, that still involve a lot of known and unknown biases. You never know what's the true mass of the cluster. Also, it may not be difficult to find large data sets, but it's very difficult to find large data sets with labels. Okay, and lastly, there are always noise and background. Some of them we understand, some of them we don't even know how to describe them. So my group has made some attempts to try to apply CNN to real observations, and as a prototype study. So this study is led by my students, Shengjie Lin and Tony Liang, and they have their goal is to our goal is to obtain relatively accurate cluster mass for a large number of clusters. So we collected a large number of clusters from SDSS, like 25,000 clusters. That's a huge amount. And we always have their optical images in 5 bands, U, G, R, I, Z, and we don't know their mass. But for a very small amount of them, like 1,500 clusters, we can get some relatively accurate mass estimates based on X-ray and SZ observations. Okay, so then we need to find a clever approach to utilize both data sets. So we use this transferring learning. It's a 2-step architecture. You can see the first step, and we train the network to predict which band are those images. Like, are they G band, are they U band, are they I band? So it's a 5-class classification. Then we train it with this huge data set. Then we take the lower level of this architecture and apply to
2.5 minutes.
Oh, okay, thank you. To this smaller data sets, we have relatively accurate mass estimate. That then we are able to predict the mass of the clusters. So I'm going to show the result that it's a huge scatter between the prediction and the ground truth. It's not beautiful, but this is a real world. And I have to say our results start to rival the performance rate mapper. That is a state-of-art algorithm to predict cluster mass from optical images. And so just to look forward a little bit, and very soon that there are going to be multi-wavelengths large cluster surveys, not only from optical images, but also from SZ and X-ray studies. And so with the coming of flood of data, and the performance of our algorithm is very likely to improve, but the performance of rate mapper is probably not going to improve much. So despite that, there remains a huge scatter in the performance of this current work. We expect that it may become better soon. Okay, Thank you. I'm happy to take questions.
Yeah, there are already a couple of questions. If you have any more, please type them in the Slack, and I'll read them out to the speaker. The Slack talk discussion channel. You can also put them in the Q&A, but the Slack is easier because then they stay around and the discussion can continue after the Zoom session is closed. So in the Zoom session, we have a question from Jeff Scargill. He asked he lists a number of things that I'll read out in a second, and asked, in your neural network application, do any of those cause any practical problems for you? In particular, like the uncertain convergence, that you don't know if it converges versus a local or global minimum. It depends on the initial state and may also depend on the structure of the network that you choose. I mean, there's a lot of choices involved, and which of those, if any, cause practical problems for the application that you're pursuing.
Thank you. So I would say we didn't deal with all those questions you brought up, but we did some tests on different networks. So like we tried a few simpler ones and some more complicated ones, but I would say this one gives the best performance so far.
Juan Martinez Galacera asks, or comments as a comment, and says, you select objects that are misclassified by your neural network, and that way you're finding anomalies. He suggested you're probably finding anomalies. So the question is, could you perhaps use like this as an anomaly detection approach to find in real observations, to find objects that are really interesting because they're not what you expect them to be?
That's a good point. First of all, it depends on ideally if we are able to truly apply to real observations, then I think that that could be that could be a very clever way to find an interesting object. So the bottom line is you think that misidentified cases are like some mistake, right? It's a bad thing, but it's not. It's maybe the most interesting thing.
I have a more technical question to your method. Since you learn on the images, like the orientation of the images may matter. There's really like the orientation that Chandra has on sky at the time of the observation is random or arbitrary. Do you take that in account in the training in some way? How do you do that? Or how do you deal with that?
We want to tell the network that the orientation doesn't matter. The cluster doesn't become a non-cool after you rotate it. Same as when you recognize a picture of a dog, and once you rotate it, it's still a dog, it won't become a cat. So when we train the network, we randomly rotate each input images. So the network knows that the rotation won't make a difference.
Are there any other questions that people want to raise? I don't see anyone typing. And we have about 30 seconds left. So thank you very much for the interesting talk. I specifically enjoyed the way you explained all the steps in the process. That is for techniques like convolution, like these networks, they're still fairly young. I think it's very important or very useful for many of us who haven't done that ourselves. Like I've read about it, I've never used one. So I appreciate you telling us how we actually get that.
Yeah, it's not a mystery. Yeah, thank you.
I would thank you for talking, and I would like the next speaker, Tong Bao, to share his slides and to get started then.
Can you see me slides now?
We can see your slides, but they're not in presenter mode yet. Now it looks good, and we can hear you, so please go ahead.
So thanks a lot for the organizers. It's a great honor to be here. I'm Tong Bao from Nan University, and my course is Li. Today I will introduce my recent work searching for quasi-periodic oscillations in active galactic nuclei of the Chandra diffuse source. I will start from the background why QPU matters and what can we obtain from the QPU searching procedure and with some simulation work. So first, let's see some examples of QPUs. We know that they are discovered in black hole binaries, ultraluminous X-ray sources, and active galactic nucleus. The exact origin of them are still not established yet, but we believe they are probably associated to disk instabilities, geometrical effects like disk precession or calipari motion near the its core. So generally speaking, it should be caused by some geometrical or dynamical effects of the inner edge of the accretion disk. So this statement stands thanks to the approximate relation between QPO frequency and black hole mass, like I show in this figure. Black hole mass would be ranging from 10 solar mass to 10 to 8 solar mass. So here we present the first dedicated search for agent QPOs in the deep field. So deep server is like change your deep field source provided as the advantage of a nearly unbiased sample of hundreds of agents at the same time. We divided the total 7 million seconds into 4 epochs. And then we apply the well-known normalized Lamb-Skagel method into all the sources, like nearly 1,000 sources and the 4 epochs. But we found no significant joining periodic signals among these. We said joining periodic signals because actually we can see that there are dozens of them are valid detections over 3 sigma significance. Here FAP means false alarm probability. But the dashed line level here represents the Chandra dueling motion period. If I remember right, it should be 700 and 1,000 seconds for respectively. But these two labeled by number is actually caused by the strong outburst at the short time scale. So both of these two types are not genuine QPOs from the agent itself. But still, actually, we can give an estimation on the occurrence rate of persistent QPOs, since we can simulate the agent light curve with or without QPO variation. And based on the large number of the simulated light curve, the detection efficiency of the searching procedure can be estimated by, here we use 1,000 fact light curves for each group of dataset. And we can barely see the QPO detection efficiency has dependence on the source count rate, the X level, and the crazy period, and the different QPO model. Model A and model B represents the detailed model for about their quality factor and advanced magnitude. I would not elaborate further in this talk.
2 minutes.
Okay, thank you. From this equation, we have the detection efficiency and the Chandra deep field source sample. And also we know that we have 0 event of QPO detection. So the occurrence rate of QPO should be constrained to be lower than about 15 to 20%. Okay, finally, I'll give a summary here. No statistically significant QPO is found on any of these 4 epochs, and the intrinsic occurrence rate is constrained to be lower than 20%. And finally, the last point I should present is that despite we have 0 detection of persistent QPO, that means lasted for at least 1 total epoch, we divided all the light curves into small subsets, and we found 2 short-lived QPO candidates. Okay, that's all. Thank you. I'm happy to have any questions.
We have almost a minute for questions. Okay. So one of the questions we have is by the Skagel. Yeah. Do your false alarm probabilities account for the colored, not the white noise, but the colored noise background on which you have below your QPOs?
Yeah, I understand you mean. Here we have we should have the agent light curves red noise because we know their observation gap. Here we use the false alarm probability from the bootstrapping method. So I think they should already, I think they should be already considered in the bootstrapping process.
Thank you. I think that answers the question. Thank you so much for your talk. If there's any more questions, please put them in the Slack channel, and we'll continue to our next. We continue to our next speaker, Hugo Tranin, and I'll give you after 15 minutes. I give you a 2-minute warning.
Okay, so
I'm not seeing anything yet. Now the other slides, and I hear you. So please go ahead.
Thanks. So hello everyone, and thanks for inviting me to present the work I'm doing for my PhD. So I am Hugo Tranin, second year PhD student in IRAP in Toulouse in France. And today I will show you 2 classification approaches we developed to mine large fractions of the Swift and XMM catalogs, but that will soon be applied to the Chandra catalog. So to this day, X-ray catalogs gather about 1 million X-ray sources, and most of them remain unstudied, as you all know. But this number is going to increase a lot very soon, considering the 30,000 sources observed by eRosita in just 140 square degrees. So, and in the X-ray zoo, you expect a majority of AGN, then stars and X-ray binaries, and then some more exotic objects like tidal disruption events, ultraluminous and hyperluminous X-ray sources, and special types of AGN, and so on. So a lot of treasures are hidden in those catalogs. And that's part of the reasons why it is useful to classify them. But first, we have to wonder which features, which data are needed if we want to classify them manually. For example, this object is a typical AGN, and I can tell you so because of all these reasons. The source location, the X-ray spectrum, the X-ray light curve on the short term and the long term between different observations, and the multi-wavelength counterparts are all important in this task. And you have about 55% of the XMM and the Swift catalogs satisfying enough criteria to be classified this way. But how can you automatize the classification? Well, I found in some first approaches in the literature, and they were always on small samples. For example, Dacheng Lin and collaborators in 2012 classified, use the decision tree to separate 3 classes, that is stars, compact objects, and AGN. And later works used the random forest method, which is more accurate, but less interpretable. So if I sum up, I can say that very few classification schemes are probabilistic, and most of them only use limited datasets, both in size and in features. Plus, their training samples contain few X-ray binaries and cataclysmic variables. Okay, so the question is, can we do better? For our sample, keeping most of the Swift and XMM catalog, we identified a training sample for these 4 classes: AGN, stars, X-ray binaries, and cataclysmic variable. And then we also identified optical and infrared counterparts. And last but not least, we gathered X-ray detections from different observatories to better assess the long-term viability, as illustrated here. Okay, so now that we have an enhanced catalog, let's look at the distributions of some features. For example, you see here the densities for the stars and the AGN of the X-ray over infrared flux ratio. So you can, well, from the training sample, sorry. You can say, okay, all sources below -1.5, for example, are stars, and all other are AGN. But this is not very accurate because there is an overlap here. So one improvement is to infer the likelihood of a value given each class. So for example, if your source is 100 times fainter in the X-ray than in the infrared, then the likelihood of the stellar class is 93%. And then you can combine it with another data, say the galactic latitude, do the math with the Bayes rule, and obtain the posterior probability of your class. And what we just built is called a naive Bayes classifier. Sorry. So, all right. So in practice, we used not 2, but about 15 features. And for each category of feature, for each category of features, that is the multi-wavelength counterpart, the variability, the spectrum, and the location, we assigned a weight here in the final formula. then we were able to optimize these coefficients in order to obtain the best results for the class of our choice. And here that is the X-ray binaries. So in a nutshell, we are left with this flow chart of the classification. You start with a training sample, you estimate its densities, you optimize some coefficients, and then you can apply the classifier to the whole sample. And it's time to look at some results. Starting with this slide. So beginning with the training sample, here is the confusion matrix of the classifier. And as you can see, AGN and stars are very well retrieved, over 99% of them, with a very good precision. And X-ray binaries show good results as well, thanks to our optimization. But that's not quite the case for cataclysmic variable. And also we compared our results with the results of a more standard random forest method, and we got a similar performance. But as we saw last week in a classification work, being able to interpret the results is as important as reaching an apparently good performance. And the good thing with our method is that for any source, you can very easily retrieve the reasons why it was classified as it was classified. So indeed, another classification product is this plot, showing the probability track, that is to say, the contribution of each property to the final probability of each class. So for example, for example, here you can see that this source was classified as X-ray binary because of its variability and also because of its hardness. So moving on to the test sample, we obtained above 75 AGN of our sources classified as, well, above 75% of our sources were classified as AGN. That's more than 250,000 AGN candidates, and 20% of stars and something like 8,000 X-ray binaries. So we verified manually the classification of 200 sources, and the classification as stars and AGN was more than 90% accurate. That's not the case for X-ray binaries and cataclysmic variable. And sorry, I have some trouble with my slides. That's not the case for X-ray binaries and cataclysmic variable, and this is because of two main reasons. Many false positives are special types of AGN and stars, like young stellar objects or very variable stars, and they are thus different than the bulk of stars and misclassified. And also, there are only a few hundred X-ray binaries and cataclysmic variable in the training sample, which may not be enough, considering their very diverse nature. So the third result I wanted to show you is about the outliers. And we implemented an outlier measure, some kind of an anomaly detection method. And it is based on the densities of the training sample still. To be simple, the lower the density of the sources at a given point of the parameter space, the higher the outlier measure. And this proved useful to isolate some special types of AGN, as you can see here, but also stars, but also to spot spurious sources and a small number of treasures, I mean rare and exotic objects such as tidal disruption events, supernovae, and so on. Okay, so now let's step back and have a look at what we achieved in comparison to the works I showed you earlier. So our sample is probably enhanced. Our classification is probabilistic, interpretable, and applicable to a large number of sources, but it is still limited by the training sample of X-ray binaries and cataclysmic variable. So my final slides are about a project we developed to overcome this issue, and this second approach made use of citizen science. So as you already know, citizen science is used in astronomy since 2007 with a website called Galaxy Zoo, which was designed for the morphological classification of galaxies. And it was a tremendous success. So not only the wisdom of crowds led to a reliable classification of about 1 million galaxies, but also some volunteers made serendipitous discoveries, like a new class of compact galaxies shown here and called the green peas. And now their classifications are used in the training samples of many machine learning experiments. But in X-ray astronomy, citizen science has never been used to my knowledge. So we developed a website called Klaxon, on which every volunteer can learn how to classify X-ray sources and actually enjoy it, hopefully. And so far, we've got about 50 users, and and they did more than 50,000 classifications. So to ensure the reliability of the results, they are first trained on known objects. And only after reaching a certain success rate, they can classify unknown sources. And we show each object about to at least 20 people to make use of the wisdom of crowds. And so this process will ensure the reliability of the experiment. And our belief is that such a citizen science experiment can be a very useful complement to machine learning when you need to enlarge your training sample. For example, as of today, we obtained about 15 new X-ray binaries candidates and some possibly new cataclysmic variables. But I would like to save time for questions. So I leave you with my take-home messages. So our code, Klaxboy, is an efficient, probabilistic, and interpretable and general-purpose classifier of X-ray sources. AGN and stars are very efficiently retrieved. X-ray binaries show encouraging results, but may require a bigger training sample. And future X-ray surveys will be a real reservoir of exotic objects that will need such a classification to be found and studied. And last but not least, we can develop some synergies between machine learning and citizen science to make the most of our beloved catalogs. So I thank you very much for your attention, and I will be very happy to take any question.
Thanks a lot. There are a number of questions already, and I'll squeeze in my one first. You talked a lot about the importance of the training sample, and you said what you're going to do to improve it. Where does your current training sample come from?
Yeah, my current training sample comes from, I don't have a slide to show it, but different catalogs of known AGN and stars. So for example, the Veron and Veracity catalog of quasars and AGN, the catalogs of AGN from the WISE selection technique, so mid-infrared selection technique. And also for stars, we made use of, general catalogs of known stars like Hipparcos and the Sky catalog of stars. And for X-ray binaries, it's, for X-ray binaries and cataclysmic variable, it's something like a dozen of catalogs from the literature identified during specific pointings and surveys. I hope that answers your question.
Thanks a lot. Yeah. Christian Schneider has a question on the Slack that came in first, so I'll ask it first. He says, can you expand on the achieved accuracy and completeness? On one slide, your number suggests that you are 99% accurate for AGN and stars, and then the manual inspection says something about 90%. How are these numbers estimated, or how they're calibrated?
Yeah, okay, so that is the results on the training sample. So these objects are already labeled and they are already well known. So they represent well a kind of brighter sources. Well, what I want to say is that the training sample and the test sample have differing properties because the training sample is made of already known objects and the test sample is usually fainter objects with less detections. So this explains most of the difference in recall and precision here. And the manual inspection was done by me and by and confirmed by my supervisors. So on these handful of sources. So this explains the difference and also the two challenges I explained earlier.
Thank you. Another question by Mara Salvato who asked in a Zoom and says, thanks for the talk, Guru. One question and one comment. The question is, you're already assuming to know the correct counterpart for the X-ray source in the other catalogs. How do you do that?
Yeah. At first, we used only a very basic correlation technique, just looking at the angular separation between the two and ensuring that it's below the 3 sigma X-ray position error. And then we used a more more fancy tool to do that, which is N-way, which was developed by Salvato and collaborators. And this maybe this is enough to answer your question.
I think that sounds very good. Yeah, if not, I copy and paste all the Zoom questions into the Slack so the discussion can continue there if after the talk is over. Pavana Haba asks, what parameters do you think are the most important ones in the classification?
The most important parameters?
Yeah.
Okay.
Like you put a number of parameters in, which ones turn out to be, you gave one example where that is example, but in general, which ones turn out to be the most important ones?
Well, in general, because we optimized classification on the X-ray binary class, my answer will focus on the X-ray binaries, and the features we used are shown here. Well, there are more than this list, but what we found is the variability features. So, for example, the ratio between the maximum and minimum flux, both inside an observation and between observations, proved very useful to label the source, to classify the source. And actually, the weights the weights obtained by the optimization show the quantitatively the difference between the different feature importance. So the variability is important, but also the multi-wavelength counterparts. And after them comes the hardness and location, except for the location in a galaxy, which is not still unclear.
Thank you. There's a number of other, I've gone over some comments and there's open questions left in the Slack. So it'd be great if you guys can get back to that, if the discussion can continue there. Unfortunately, we'll have to move on to the next talk. Thank you for leaving so much time for discussion. I think that's really useful. And we still didn't get through all of them. So I would like to ask the next speaker to share her slides, which is Serena, and she is going to talk to us about BA X-ray binaries. And so we see your slides, not yet in presenter mode, but they're there. And so please go ahead when you're ready.
Yeah, thank you. Okay.
Looks good now.
Perfect. Thanks to organizer, first of all, for having given me the opportunity to talk about my BX binary project. I would also like to thank all the people listed here who are my collaborators on this project. And yeah, so I will be talking about BX binaries in the Small Magellanic Cloud as indicators of mass transfer efficiency. And if you like to check out, to know more about this project, please feel free to check out our paper here. And if you have any questions, you can feel free to contact me on both on Slack or on this email address here. So the main goal of the project is to try to learn something about binary evolution by comparing observation with predictions. And the first question, of course, is why should we care about binary evolution? And well, binaries are really an important topic in astrophysics, whether you're you're studying gravitational waves, massive stars, or even chemical abundances in galaxy evolution. It is by now clear that you need to account for the effect of stars being in multiple systems. Unfortunately, though, there are still a lot of uncertainties in binary evolution, and here I just listed some of them. So to tackle some of these uncertainties, we decided to focus on a specific population of systems, and in particularly the BX binaries. And to tell you what BX binaries are, let me start by saying what are BE stars. So BE stars are hot main sequence stars, which are rapidly rotating. And this rapid rotation, in combination with other effects, determines the formation of a decretion disk that we can detect. And so BX binaries are therefore high mass X-ray binaries composed by a BE star and a compact object, which is accreting from the decretion disk of the BE star, and in this way emitting the X-ray that we observe. And when the compact object has been identified, usually the nature of the compact object has been identified to be as a neutron star. And as I mentioned before, so we are trying to learn something about binary evolution by doing this comparison between simulation and observation. And in practice, this means trying to answer the question, can we understand the main properties of the observed BX binaries? And yeah, so again, we need this comparison between a synthetic population of BX binaries and unobserved ones. And in particular, in this project, we focus to the observed population presented in the catalog by Cohen-Kirk 2015, which includes the information about 69 BX binaries, including neutron stars, which have been detected through observation by different instruments, including Chandra. And actually, Chandra has been really giving an important contribution to this catalog, as it allowed to detect some of the widest systems that were present in the catalog. And we are comparing this observed population with a predicted one, which comes from the population synthesis code COMPASS. And if you can think of population synthesis code as black boxes where we can put our approximated understanding of binary evolution plus some assumption and simplifications. And so the study seems to indicate that most of the BX binaries have experienced a stable phase of mass transfer. So this is what is the suggested typical formation channel. So the most massive stars of the binaries will expand quicker and fill its Roche lobe. The Roche lobe is the region around the star where the matter is gravitationally bonded to the star. And when this happens, some of the matter will be lost by the star, which we call the donor, and may or may not be accreted by the companion star, which we call the accretor. And then this initially most massive star will end its life as a neutron star, which will be in a system with a BE star. And so the typical timescales of this stable mass transfer phase are enough to allow a considerable mass to be transferred from the donor to the accretor. And this fraction of mass which has been transferred is what we call the accretion efficiency, and is here represented by this beta parameter. And what we find is that this fraction is actually higher than previously thought, and that actually most of this mass transfer should be quite conservative. And of course, actually, the story is much more complicated than this. And so this is indeed, so on the right here, you see a list of observable that would be very useful for us to constrain our models and be able to learn even more on binary evolution through this observation of BXA binaries. And let me just conclude by saying the last point is that we found is that we can explain the abundance of BXA binary in the small Magellanic Cloud through the peak of the star formation together in combination with low angular momentum losses. And this point actually inspired a Chandra proposal, which is called testing the age hypothesis for BXA binaries, which has been recently approved, recommended for the Chandra program by the stage 1 panel review. And with this, I'll thank you for your attention. And please, if you have any question, contact me on the Slack or again at the email address. Thanks.
Yep, thanks a lot for your talk. I'm looking forward to see what the observations will show when they come in. We are through the 5 minutes, so any discussion will have to happen on Slack. And I would ask the last speaker of the session, Victor, to bring up his slides and get started. We see your slides. They're not yet in presenter view, but I see you're working on it. Looks good. Okay. So
Thank
please
you.
go ahead.
Thank you, Moritz. Well, it is a pleasure to be here with you all. I'm Samuel Perez. I am an applied mathematics and computer science student at the Universidad del Rosario in Bogota, Colombia. And today I'm going to present to you the project that we are doing for my undergraduate thesis, which is called Unsupervised Machine Learning for the Classification of Astrophysical X-ray Sources. And this project has been supervised by Rafael Martínez Galarza from the Center for Astrophysics and Alexander Caicedo Dorado from the Universidad del Rosario. Thank you to the organizing committee. It is a great pleasure to be here, and I'm very happy to present the work with you all. So let's start talking about a little bit about the challenges of classification. So we have seen some serious efforts and very successful efforts on providing a supervised learning pipeline for the classification of X-ray sources. Though when using supervised learning, we have many challenges to overcome, as many authors have said. For example, one of them is the lack of optical counterparts. But when we have them, as you may see in this example at the right, where we have the optical magnitudes versus the fluxes in X-rays, we could see that we could separate the classes. Actually, we could identify very good them. But even though that we have optical counterparts and we have classes here, we can find an overlap between those classes. So that's another challenge from the supervised classification. First, we have the lack of optical counterparts, but then when we have the optical counterparts, we could find some overlaps that we want to overcome. Other challenges of classification too is that we have, of those with optical classification, there is a significant imbalance between classes. And as we have seen, for example, with the George Washington University group that have been doing an amazing job in providing a pipeline for supervised classification, they have said, though, that we have this particular challenge to overcome, that is that we have many classes underrepresented in the dataset. And for example, here we have more than 1,000 AGNs, but less than 100 low mass X-ray binaries of neutron stars. So those are that is a great imbalance, and that is a challenge to overcome in the supervised classification. And that is actually our motivation that for the work that we are presenting here, a new approach of that classification. So we have seen that it is hard to classify sources in the X-ray catalogs, right? Yet we want to do it, of course, and we have seen many efforts here in the conference, because classification of serendipitous sources detected in X-ray catalogs is very important to pinpoint exotic phenomena such as GRBF glows, stellar flares, luminous X-ray binaries, obscure AGNs, etc. So many of the sources, as we know, of the catalog of X-rays have not been classified or studied in detail. That's a clear motivation for classify as many catalog sources. In this case, particularly, we are working with the Chandra source catalog as possible, both on the galactic plane and outside the galactic plane. So our approach in this case, following the motivation that I presented you before, is to use unsupervised machine learning. So we have several questions here. So given the challenges of supervised classification that I presented to you, can an unsupervised approach be used instead? Another question is that to what extent we could use just the X-ray information from the catalogs, in this case, the Chandra source catalog. How could we use that and can be used to provide a probabilistic classification of Chandra source catalog, in this case, sources. And this is part of the ongoing work, but this is an important question too that we want to answer, is that to what extent does optical information improve classification accuracy? So we say challenge accepted to this important task. Fortunately, we do have several wonderful catalogs of serendipity sources, such as the Chandra source catalog, such as the XMN catalog, and soon we will have the Rosita catalog of sources, which will cover all the sky. So that's very important. The efforts that we are doing here right now with the catalogs that we have will be very important for the science of the future with Rosita catalog. Okay, so I introduced you the project, and I want now to talk about the data that we are using. And the data that we are using is the Chandra source catalog, as I said, and this is one of the most important X-ray sources catalog, which covers more than 300,000 unique compact and extended X-ray sources in the sky. And we have more than 900,000 individual observation detections. And with those observation detections, we have many properties. For example, photometrical properties, the one we have here. We have spectroscopic properties too, such as the hardness ratios. And we have intra and interior observation variability measures. And of those measurements that we have, we could extract them from stack detections the stack detection basically covers many images in the same region in the sky before we detect the pre-observation detection for each sources. So with that, the stack detections, we could extract leisure scale variability information because we could observe how a particular source could vary in the different observations that we are stacking. But we have, if we want to have a short scale variability information, we could go directly to the per observation detection. And here I show you a little bit of like a summary of the hierarchy of the Chandra source catalog. And in particular, when we have a particular observation detections, here I show you a plan of the X-ray luminosity versus the variability time scale. Mostly the typical duration of the Chandra source catalog fall in this range that you see here in this black rectangle, which is mostly on 5,000 to 50,000 seconds in lifetime. And if you can see here in the lifetime, in that time scale, we could find many kind of sources like registers, X-ray binaries, AGNs, GRB afterglows, etc. So it is very important, and that's why we are using here the pair observation detections. For our project, we are going to use the pair observation detection because even though we are in a short scale variability term, we can find many kind of sources. Okay, so now I'm going to present you the pipeline that we are using in our project. I'm going to follow each of these boxes. So first of all, we did a data acquisition over the Chandra source catalog. Then, after having the data needed for the project, we will do a normalization or a log transport and normalization for some of the properties. Most of the properties have to be normalized because, as you may know, some properties represent variabilities, probabilities, some others represent extents. So we have different scales here. And a log transformation is needed for other sources that have extreme values and that we want to skip the skewness of the properties of the data. So after that we have normalized the data, we can apply an unsupervised machine learning algorithm. And after that we have used the unsupervised method, we could analyze these clusters by statistical knowledge by seeing what how the clusters are performing and what they are separating. Like if the clusters are separating the sources by their properties, for example. After that, we have analyzed those clusters and find out that we have a very interesting separation of the sources. We could cross match those sources with SIMBAT in order to extract the types that we need for our approach for the classification. After that, we have the types of the classes. We could analyze how those classes are distributed in each cluster. And we could find, for example, predominant classes in one cluster and predominant other classes in other clusters. So after that, we have that, we could assign a type to sources that did not find any type in SIMBAT or found like an ambiguous type. And we could do that by similarity analysis, which is based in distances. Okay, so I'm going to talk about a little bit about the data that we use and the properties that we use actually. As you may see here, we use mostly properties related with variability. And in this case, we use properties related to the spectroscopic measurements, for example, the hardness ratios. We use properties related to the strength, such as the source area, related to the temperatures, such as BBKT, related. Those are very important for the variability, the intra-observation variability. We have many properties here and features of those properties like the standard deviation, the mean value, the maximums, the minimums. So these are the properties that we use in our work. And when we see a particular projection of that property space, for example, here we have the hardness ratios between the medium and soft band, and the hardness ratios between the hard and medium band. And we have color coded the sources by the variability probability in the broad band, in the hard band. And you could see, for example, here that we have a correlation, like a kind of a correlation, a functional relation between those variables and those particular properties. As you may see here, for example, in this particular part of the graph, we have low variability sources, but if we go to the top, we can find very variable sources equally to the bottom of this graph. So we want to understand then and exploit those differences and exploit those relations between the properties to have a better classification with an unsupervised machine learning approach. So what we use in our pipeline are these two methods, basically the k-means clustering algorithm and the Gaussian mixture models. And we are going to start with the k-means algorithm, as you may see here in this GIF. Well, the k-means algorithm is one of the most important, or one of the most known unsupervised machine learning algorithms. First of all, for the k-means iteration, we have to specify how many clusters that we want in our model. For example, here we have 4, and that's actually the value of k. And we have to initialize the centroids, which are represented here by the x crosses, the y crosses here. When we initialize those centroids, we are going to assign every point of the data set to their closest centroid by the Euclidean distance. And after that, we have assigned every cluster, every point to a cluster. We could redefine the new centroids by performing a mean between each cluster. So that's what we are seeing here until the convergence. So after we perform a k-means algorithm, and after we decided some parameters, for example, the number of clusters by empirical knowledge, because we for example, in here, we are using k equals 6, and that's because by doing many experiments, we found out that this separation gave us an interesting characterization of, for example, you could see here in the left graph, you could see that the sources in the galactic plane are separating from the sources outside the galactic plane. So we could find that even though that those are separating, that those are different clusters from the outside out of the galactic plane, we could find that we have many clusters many clusters represented in the galactic plane. And we could see that that separation of the properties in the clustering by looking again at the hardness ratios. As you can see here, the hardness ratio in the medium and soft band, and the hardness ratio of the hard and medium bands. And we could see that, for example, some of the clusters tend to be very hard, and some of the clusters tend to be very soft or be in the medium band. So that's interesting. We are seeing a clear separation of the properties. But when we k-means, we have a lack of flexibility in cluster shape. Since we assume when we are doing k-means, we assume that we have spherical shaped clusters. And additional to that, we have a lack of probabilistic cluster assignment because we are performing a hard clustering technique. So we decided to migrate the analysis to a more scalable approach, which is the Gaussian mixture model that is more flexible and more general than the k-means algorithm. And the Gaussian mixture models are actually very related to the k-means algorithm, since, for example, we could say that the k-means algorithm is a particular case of the Gaussian mixture models. And for example, here we are not assuming that we have spherical shaped clusters, but we are assuming that all clusters are distributed by a Gaussian, but we don't know the parameters of those of that Gaussians yet. So for finding those parameters, we are going to use a very known algorithm called as expectation maximization, which is gonna maximize the log likelihood to find those parameters and to finally fit those Gaussians to a interesting cluster, as you can see here, until convergence, of course. And as you may see here, we have a plot again of the hardness ratios between the hard and soft band and the hard and medium band. And as you may see, the algorithm actually tries to separate the clusters according to their X-ray hardness ratios. And for example, you can see the stars are representing the centroids of each cluster, and we could see a clear separation again of those clusters.
2 minutes.
Thank you. We could see that again. We could see that again in the separation of the clusters. For example, we have very soft clusters, and we have, for example, very variable clusters too, and we have very clusters that are very low variable. So that is interesting because that is saying to us that the separation of the clusters is not coming by magic, but they are coming by a clear separation of the properties. So after that, we cross-matched the clusters with SIMBAT, actually the sources, all of the sources that we had in the data set with SIMBAT, and we cross-matched with that with SIMBAT in the sake of the classes of already clusterized data. So after performing that cross-matching, we find out that approximately 44% of the data didn't find an unambiguous or any match at all. So we have a lot to do, almost the half of the entire data set. And when we have done that cross-matching, we could find that we have some sources that are very dominated by, for example, Orion B stars or YSOs or T Tauri stars that are joint stars, and other clusters, for example, the cluster 5 dominated by Seyfert-2 galaxies. But in those clusters, we have a lot of sources that didn't find any matching type. So those sources and the ambiguous ones, like the stars or X-ray source, we want to classify by doing a similarity analysis. So we have those source observations that did not find any ambiguous class in the SIMBAT cross-match. How do we classify them? So we are performing distances here. And by performing distances, what we want to do is to use the Mahalanobis distance, and that's because it gives us information. This Mahalanobis distance gives us information about the correlation of the point that we are trying to find the distance and the distribution of the subset that we are looking for. So for example, here you could find that these points are in the same Euclidean distance, but the blue points are actually closer because they are correlated with the distribution. And after that, we want to do Mahalanobis distance between the subsets in each cluster. This is a particular case of a cluster. So we have YSO, Centauri stars, VY Draconis stars. And first, we want to compute the mean Mahalanobis distance between a non-classified register as the black one in a cluster to every observation in a classified group of the cluster. For example, YSO, Centauri, and VY Dra. After we have those mean distances, we can perform a submean function in order to assign probabilities. And the closer the point is to a subset, means that it is more probable to belong to that subset. So I'm going to present to you right now the results. And following this process, we can self-assign a class to a non-classified source depending on the non-classes of its cluster. So we have a probabilistic output, and we could reveal some interesting classifications from our output. For example, here we have this source that we found in the first cluster, and this source is classified as BY Dragonis star. And we can see, for example, here the probabilities of the most predominant for the most predominant classes in the cluster. For example, we have BY Dragonis, Candida YSO, Orion B stars, T Tauri stars, YSOs, and we could see that by our model we could find that it is very probable that this particular source is a BY Dragonis star. And when we see it in for example, in ESA sky, we could find that it is actually located in the Orion Nebula, which is a star formation known place. And other sources, for example, we have other sources like this one in the cluster 5, which is classified as a Cipher-2 galaxy. We can see here that it is very probable from our model that this model is classified as a Cipher-2 galaxy. And when we look for it in the ESA sky, we could find that it is actually in the center of the Perseus cluster, which is a non-galaxy cluster. So this is saying to us that this is a galaxy, but it is a specific kind of galaxy. So that's very interesting. That's a very interesting output of our model. So for each source observation that does not have an assigned class, we will provide a probability over classes. We have just shown you just 2 examples of those sources that we want to classify, and this will be the main output of our algorithm. So in conclusion, we have demonstrated an unsupervised approach for the classification of X-ray sources. We use both k-means and Gaussian mixtures. We assign probabilities by a defined distance metric and pipeline. In this case, we assigned those distances by the Mahalanobis metric, and then we use the submean function. We find that this analysis is consistent in expectations in terms of the cluster membership. We have found that they are separated, the clusters are very well separated by the physical properties of the catalog. And we want to present, and we will present, a full list of classes for all the X-ray sources in the Chandra source catalog too that don't have currently an assigned class. In the future work, we want to cross-match or Chandra source catalog sources with the SDSS optical information, and maybe we will add that optical information to our pipeline. But we want to explore the possibility of performing semi-supervised techniques when we have those optical information, because those optical information could give us more information about the classes of known sources. We want, of course, to do an analysis of typical observations that were misclassified because the model is not perfect, and we have found other sources that were actually in places that doesn't make too much of a sense of the classes that they were provided. So that's kind of it. Thank you, and I will be open for questions.
Thank you so much for your talk. I first need to apologize. Unfortunately, I gave my 2-minute warning a little too early when you really still had 7 minutes left. I think you realized that.
Yeah, I was
sorry about that.
Don't worry.
Sorry about that. So a question by Johannes Buchner. He says, nice approach. Do you use observation about how the observation was taken? For example, the exposure depth or the galactic latitude? And would it be worthwhile, in addition to that, would it be worthwhile to use the spectral fits, which may be more stable than the hardness ratios? Because the Chandra source catalog has spectral properties fitted to it too.
Thank you. Let me read again the questions. Was taken. Information about how the observation was taken. So yeah, well, we are using just the information about the source specifically, like actually I shown all the properties that we use in our method here, and those are more related with variability, with the spectroscopical measurements, and for example the hardness ratios. We have some properties related to the strength and the temperature too. But yeah, to my knowledge, we don't have use information about how the observation was taken. For example, the lifetime. We haven't used that yet.
Sounds reasonable to me, since there's clearly going to be a bias in how people write certain proposals. Right? Oleg Kagaltsev asked in the Slack, he says, it's a nice talk and interesting approach, Victor. What do you think is the main advantage of your unsupervised approach in comparison to the supervised approaches that people have discovered, that people have discussed in the previous talks? What's better? What's worse using unsupervised versus supervised methods?
Well, yeah, but as I said here, we have many challenges to overcome in supervised learning. And it's very interesting that, for example, we provided here probabilistic classes without having a training set. And that is something that we kind of are grateful of, because we didn't have to we didn't have to construct all the training set for classification. And what we are doing on supervised approaches, we could, for example, we could use just the X-ray information that we have here. And that's very interesting, because when we are doing, for example, supervised classification, we need cross matches with sources that have actually classes. So I think that it is a kind of a good point from the unsupervised classification and unsupervised approach, that we don't have a training set, we don't need a training set, and we can perform the model with all the sources that we have provided, that we have this available in the Chandra source catalog. Did I answer the question?
Sounds good to me. If not, the person who asked, you can always post a follow-up question on Slack and start a thread.
Of course.
A question by Yang on Slack. Do you have any comments on the accuracies or inaccuracies of the SIMBOT classification? That's something that I've myself seen before. Like you have these ONC stars, you have the YSOs, you have T-taris, which are kind of almost the same thing, except that for some reason SIMBOT thinks they're different classes. And I'm sure that happens in other fields too. Do you have any comments on what that should?
Yeah. Yeah, they give multiple classification for the same source. Thank you, Huiyan. Thank you for putting that in the table. We have taken mostly the main type that is classified in SIMBAT database, and we haven't actually analyzed a lot about the accuracy of those classifications. And for example, but we have known that those classifications, and most of them are not very, or a lot of them are not very good. For example, we have ambiguous classifications, as I say here, and those ambiguous classifications, we want to provide a probabilistic classification to them based on our method. For example, we have the X-ray source classification. We have the unknown classification too, and yeah, you could find that actually here in the tables that I presented. So we have, for example, the star, that is a kind of an ambiguous classification from the SIMBAT database, but we are taking on account those classifications. We are taking on account those sources that classified as that, because we find that an ambiguous classification, and we want to have a probabilistic assignment by our method.
A similar question that just came in on the Zoom is, do you find any source types that you essentially see in every cluster? So the things are that you can't really classify, that turn up everywhere, and that just don't cluster very well in the parameter space that you're using?
You mean the question from Solen Ballman?
Yeah.
Okay. I think that I don't get your question very good.
Well, let's say there is some type, let's say QSO. It's probably not that, but that turns up in all 6 clusters. Do you have anything like that? Anything that turns up in every cluster, essentially?
Yeah, of course. We have many sources, many kind of sources that appear in other clusters. For example, we have YSOs appear in most of the clusters. So those are very interesting. But what we are trying to do is we know that we have contamination in our clusters, of course, and we have classes that are contaminated in our clusters. But for that, we are taking the most prominent classes in our cluster. And for example, in the cluster 1, for example, in the cluster 0, we have Orion B stars, YSOs, T-Tauri stars. But then if you go down, you will find high mass secondary binaries. But we are taking this cluster, for example, taking just the 5 most predominant classes, and in order to say that this cluster is dominated by, for example, joint stars.
Thanks a lot. That was an interesting talk and a good answers to all of these things. I've seen that there's some of the questions have sparked further discussion, and there's going to be some talk going on Slack, which of course all of you can continue after the Zoom session closes. I want to thank all of the speakers in this session again, including Victor and all the previous speakers. We have the next session in about 30 minutes at 12 o'clock Eastern time, using the same Zoom link. And we welcome everyone to come back to that. I want to announce one more thing. We've been asked to provide, or if we have a more social meeting place, like in a normal conference, you would now walk out and get your coffee or get your lunch and run into other people. So we've set up 2 rooms on Mozilla Hubs. The link is on the Slack and the general channel, where you will walk around or can walk around with an avatar in 3D through like a hall or on a beach or something, and just ran into people and chat. Some more instructions are on there. Each room holds up to 25 people, but we only have 50 people listening right now. So if you can't get into one, just try the other link. If one is empty, just try the other link. Maybe everybody's congregating in the other one. Those rooms are open 24/7. So you can join them now for your coffee, or maybe just before or after a session, we probably have the highest chance of running into anybody. If you have any technical problems with that or questions, I added a coffee channel to the Slack that I'll try to monitor and answer questions. And then here on Zoom, we'll see you back in 28 minutes. Thanks a lot, everybody, for listening and for talking.